In this lesson, we're still going to be talking about exponential functions. We're going to look at the third way that exponential functions can be applied, and that's with geometric sequences. We've learned about sequences in the past in elementary school. This sequence and another sequence we'll be looking at this year work a little bit differently. A geometric sequence is going to be a sequence of numbers in which the ratio remains constant. So geometric sequences, we've seen them before. We've just talked about them in different ways. So a geometric sequence might be 2, 4, 6, 8. So it's going up that constant ratio. Now, the constant ratio you can find, it's found by dividing each term by its previous term. And that will tell you what that constant ratio is. And once you know that constant ratio, you're more able to finish the sequence. So the first thing we want to be able to do is to identify if a sequence is a geometric sequence or a different type of sequence. So what we want to do on number 1 is we want to take a look at the sequence 2, 10, 50, 250, so on. And we want to determine that common ratio, and if there is one, we know it's a geometric sequence. We're going to determine that common ratio by dividing each term by its previous term. So we're going to work backwards. So when you take a look at the end of this ratio, 250 divided by the previous term, which is 50, tells me that that common ratio is 5. Then if I keep working backwards, 50 divided by its previous term of 10, 50 divided by 10 is 5. And then 10 divided by its previous term, 10 divided by 2, is also 5. So since that ratio is the same throughout the whole sequence, then we can say, yes, this is a geometric sequence with a ratio of 5. We can do the same thing with sequences that go down. So number 2, 135, 45, 15, and 5. We're going to do the same process. We're going to start at the end with 5 and dividing it by its previous term. So 5 divided by 15 gives us a fraction of 1/3. Then 15 divided by its previous ratio. 15 divided by 45 is again 1/3. And then 45 divided by 135 is also 1/3. So that ratio is the same throughout the whole sequence. So we can say, yes, it is a geometric sequence with a common ratio of 1/3. Number 3. We're going to do the same process, starting with 30 divided by its previous term of 24. 30 divided by 24 has a ratio of 5/4. Then 24 divided by 18 has a ratio of 4/3. As soon as you get a ratio that is not the same, you know that this is not going to be a geometric sequence, and you can stop. Go ahead and highlight 4, 5, and 6. And then let's take what we know so far about common ratios and continuous sequence. So we know these are geometric sequences. We just want to continue it with the next 3 terms. So we still want to find that common ratio because that common ratio is going to help us find our next term. So on number 7, starting with 63, 63 divided by negative 21 gives us negative 3. Negative 21 divided by its previous term of 7 also gives us negative 3. And really, I should have only done that once because I already know it's geometric. So I know that common ratio is negative 3. So to move forward with our sequence, we want to multiply. So to get our next term, we're going to take 63 times negative 3. That gives me negative 189. And then negative 189 times negative 3 gives me 567. Then 567 times negative 3 gives me negative 1,701. Go ahead and highlight number 8, and let's look at number 9. So again, we want to find the common ratio. So starting with 2 divided by its previous number of 4, that gives me a half. So my common ratio is a half. So to move forward with our sequence, we want to multiply each term by a half. So 2 times a half is 1. 1 times a half is 1/2. And 1/2 times a half is 1/4. Go ahead and highlight number 10. Now, not all geometric sequences are so small. Sometimes when you have a geometric sequence, you want to find a number that's not within the next 3. You might want to find the number in the sequence that is way down the line. And you don't want to take the time multiplying that ratio over and over to find that. And when you have a situation like this, there's a formula that you can use. So the formula that you're going to use with geometric sequences is going to be A sub n equals A sub 1 times r to the n minus 1 power. Now the A sub 1, that's going to be the first term in your sequence. So you can replace that with the first term in your sequence. The r is going to be that common ratio. So when you divide a term by its previous, that will give you that ratio. And then this n here, this should just be replaced with the number you're trying to find in the sequence. So for example, with the next few we look at, it wants us to write the rule. So we're substituting it into the equation and find the A sub 7. So we're finding the 7th term in the sequence. So looking at number 11, because we're working with geometric sequences, we're going to start by writing that rule. A sub n equals A sub 1 times r to the n minus 1. And we need to write this for every problem to help us remember it. And then we need to identify what A sub 1 equals and what r equals. So A sub 1 is the first term in our sequence, and the first term is 3. And then r, to figure out what it is, we take 27 divided by 9. And 27 divided by 9 is 3. So r equals 3. So now that we know those two things, we're going to substitute them in our equation where A sub 1 and r are located. So rewriting it, A sub n equals 3 times 3 to the n minus 1. So this is the first part of our answer. This is the rule that they're looking for. So your rule should always have the 2 n's still left in it. Now when we apply the rule, we're going to replace those n's with the number we're trying to find in the sequence. And per our directions, we're finding the 7th number. So we're going to rewrite it, but instead of n, we're going to put 7. a sub 7 equals 3 times 3 to the 7 minus 1. And then we're going to solve it. As we solve it, the a sub 7 over here on the left, it doesn't really do anything. It's just a notation to show you that you're finding the 7th number in the sequence. So we're just solving the right side of our equation. So that would be 3 times 3 to the 6th, because 7 minus 1 is 6. And 3 times 3 to the 6th, we can put this in our calculator, is 2,187. So that would be the 7th number in this particular sequence. So I've written a rule that can find any number in my sequence, and then I use the rule to find the 7th number in my sequence. Number 12, we're going to do the same thing. My directions still tell me to find that 7th number. So we're going to start with writing the general formula. A sub n equals a sub 1 times r to the n minus 1. Then we're going to write what a sub 1 equals and what r equals. So a sub 1, our first term, is negative 4. And then remember, to get r, we take negative 100 divided by its previous term of 20. And negative 100 divided by 20 is negative 5. So r is negative 5 and a sub 1 is negative 4. And we're going to replace that in our equation. So a sub n equals negative 4 times negative 5 to the n minus 1. And we're going to put that negative 5 in parentheses. So this is the rule that we're going to use to find the 7th number. So we're going to find a sub 7 equals negative 4 times, in parentheses, negative 5 to the 7 minus 1. That would be a sub 7 equals 4 times, in parentheses, negative 5 to the 6th power. Make sure that negative 5 is in parentheses, especially when you put it in the calculator. Because when you calculate negative 5 to the 6th power, if it's not in parentheses, you get a different answer. And when I calculate that, I get 62,500. That would be our 7th number in the sequence. On your next page, go ahead and highlight 13 through 18. And keep in mind, as you do these, you're doing the same process. And it is okay to get positive numbers, to get negative numbers, to get fractions, and to get decimals as you're working and for your answers. So don't let those deter you from being confident in your answer. The last thing we're going to do is look at an application problem. So geometric sequences applied to a real-life situation. The table to the left shows a car's value for 3 years after it's purchased. We want to write a rule to represent the car's depreciation and then use it to find the value of the car after 10 years. So after 1 year, the car is worth $10,000. After 2 years, it's only worth $8,000. And then after 3 years, it's only worth $6,400. So we're going to first write the generic form for our geometric sequence. A sub n equals a sub 1 times r to the n minus 1. And we're going to write what a sub 1 and r equal. So the first number in our ratio, as we look for our ratio, we're looking at the value. Okay, we're looking at just that column. So the first number is 10,000. And then to get our ratio, we're going to take 6,400 divided by 8,000. And we do get a fraction. So our common ratio is 4/5. So when we substitute those into our equation, we can write a rule that says a sub n equals back up, equals 10,000 times 4/5 to the n minus 1. So this is going to be our rule that we can use. And we can use this rule to find the value of the car at any time. But the problem wants us to find the value of the car after 10 years. So we're going to be using the rule A sub n equals 10,000 times 4/5 to the n minus 1. But we're going to be replacing our n's with 10 because it wants to know how much after 10 years. So that would be A sub 10 equals 10,000 times 4/5 to the 10 minus 1, which would be A sub n equals 10,000 times 4/5 to the 9th. And from here, you can put it directly in your calculator. Now remember, we're talking about money, so you want to round to 2 decimal places. So that would be $1,342.18. That would be the value of your car after 10 years.